Hi, this is the Tier 3 Fuel Injector Side Pipe Disassembly Station team. We were sponsored by Bosch, and the team consists of me, Morgan Abbott, Zach Kaiser, Alex Landit, Gabe Momber, and Kendall Oleski. Our advisor this semester was Dr. Pung. Today we will be going over the problem statement, the description of the problem, the scope statement, key specifications, the concept designs we had, different design details, and design challenges that we overcame. Okay. The purpose statement was to design a disassembly station for the Tier 3 fuel injector side pipe to allow for remanufacturing of the assembly. Pictured is a full assembly of what we were challenged to disassemble. The scoping statement objective was to design a disassembly station for the General Electric Tier 3 side pipes while maintaining Bosch safety standards. They gave us a budget of $20,000, and from the side pipe assembly, we had to recover the outer sleeve, the high pressured shaft, the T-piece, and the left-hand nut. The design must be capable of removing the left-hand nut, assist in the O-ring removal, pull apart the outer sleeve from the T-piece, unthread the T-piece and high-pressured shaft from one another, and be able to disassemble the side pipe at any state of partial disassembly and continue in the process. Below is a disassembled picture of the side pipe assembly, along with the parts that we needed to keep. Are scrap pieces shown, which include the ball and spring and O-rings.
For the selected concept for removing the left-hand nut, we decided to use an impact driver. The requirements for this impact driver is that it needs to supply a 90 Newton meter torque. It does not need to. It needs to apply. It cannot apply an excessive torque on the user and can only rotate in one direction. The negatives of this is that the battery charging is required. However, the positive is that it's small, it's cheap, it's easy to learn and use, and it's easy to get off the shelf, and it's used at many stations already. In order to remove the O-rings, we decided to go with a V-shaped tool in order to push down on with the outer sleeve and push that O-ring up to making space for that cutting tool to cut through that O-ring and remove it. The downside of this is that there's a pressure required from the operator, but the positive is that you can use it for both O-rings, and there's an ergonomic advantage for the operator. In order to remove the outer sleeve, we decided to go with a U-tool with a pneumatic cylinder. We would need to supply an estimated 180 newtons or 40 pounds of force in order to remove that O-ring press fit, and it must engage with two-hand operation. The benefit of this is that it's cheap, it's clean, and it's easy to get off the shelf. However, it increases the space requirements as well as requires a two-hand safety feature. In order to remove the T-piece from the inner shaft, we decided to go with an electric motor. The requirements for this is a 650 Newton meter torque. It needs to be ergonomic and it must be robust. The downside of this is that it increases the cost and requires two-hand safety. However, it is powerful, repeatable, it's easy on the operator, and it's quiet as well as it's easy to power. For the overall selected concept, we created a CAD representation, which you can see over to the right on this slide. The first step would be to remove the O-ring, which we would do so with a push down and cut manual fixture. A left-hand nut removal, which would consist of the use of an electric impact driver, and the removal of the outer sleeve, which is done via a pneumatic cylinder, and the separation of the T-piece and the high-pressure shaft, which would be done with an electric motor. The advantages of this is that it simplifies the operator's actions, it minimizes the force required from the operator, and it reduces the overall cost.
Looking at our overall design, a space usage diagram was created to give an idea of what space we will actually be using. As seen in the figure on the left, our station will be about 1,220 millimeters wide by about 647 deep, with an overall height of 270 millimeters. Each process of the disassembly is shown, so each station. In the green, we have the first station, which is about 375 millimeters wide. Then we have the V tool to remove the O-rings, which is about 150 millimeters wide. And the orange box shows the high pressure shaft removal station, which is 375 millimeters wide as well. With little testing, we were able to create what we would believe would be a timing diagram for the whole process of disassembly of the Tier 3 side pipe. The figure on the bottom shows our estimated time for a new user of this product and how quickly they would be able to do it. Adding all this up, we have a time of about 3 minutes and 25 seconds to fully disassemble a Tier 3 side pipe assembly for a new operator of the station. As previously talked about, going a little more in depth on our process chosen to remove the O-ring, we created a 7-gauge hot rolled steel V-shaped tool, as we call it. This is nice because it does allow for the removal of both O-rings, even though they are different diameters. Pushing down into this allows for cutting of both O-rings. Moving on to our outer sleeve removal station, we are using a pneumatic cylinder as well as 2-hand touch controls to remove the outer sleeve from the T-piece. This is done after the impact wrench is used to remove the left-handed nut. All this is held down with a spring-loaded pin to keep it from moving while the operator is doing so. Our third and final station is the T-piece and high pressure shaft separation station. As seen in the figure, we have created a wrench that will provide the necessary torque of, we needed at least 615 newton meters. We will be supplying 678 newton meters of torque. We will be doing this with the use of a Nord gear motor and a Leeson 2-horsepower motor. These will both be controlled electronically with Banner 2-hand touch controls system with a safety relay, which is shown in the lower left-hand corner.
The second half of that is requiring hanging on to the high pressure shaft so it does not rotate as the T-piece is twisted off. And so we came up with a linear slide and hex socket assembly, as you can see here. This allows the hex socket to move up and down and to slip over the high pressure shaft when it is placed in the vertical position. But when locked into place or put in its lower position, it will properly secure the part so that it will not rotate, twist, or deform during the removal process. And the linear slide makes it easier for the operator to move this piece up and down without putting additional strain or additional harm to their back while using this piece of equipment. In order for all of our electric components to be wired correctly, we came up with a wiring diagram. We selected for the system to be run on 110 volt VAC, and that will also have additional outlets for plugs that will allow the users to gain additional access to power down the road if there are changes or updates that need to be made to the system. We also implemented, like what Zach had mentioned, a 2-hand safety system, and this will run on 24 volt DC. This allows the system to be completely safe and remove the operator from the potential of being shocked by 110 volts if something was to go terribly wrong. And the wiring diagram on the right has all of our major components listed, as you can see there. We also have our gauge of our wire listed and any fuses that would be required, giving a complete picture to any type of electrical questions that may be needed to be answered down the road. All of those electrical components come back to a panel. This is where everything will be fused together or mounted so that there's no access to the operator. And as you can see on the right side, this is laid out with all of them in order, and this would be the way you'd actually see the panel. And on the left, there's a bill of materials listing what each one of those are, along with part numbers and a description. This makes it easy for anyone to take a look at the panel and understand what is going to be doing what and how to fix it if something goes wrong as well. In order to complete two-hand safety for our pneumatic system, we need to come up with a diagram here as well to make sure that is run correctly. This is going back to our outer sleeve and T-piece removal. So in order to move that cylinder that will pull those two apart, we need to have a two-hand safety. So this is laid out here, obviously using pneumatics, which makes it easy and safe for the operator, as well as this drawing gives us an opportunity to make sure everything is in working order, and if something was to go wrong, parts can easily be replaced down the road.
This project had a number of design challenges associated with it. The tool used in removing the outer sleeve was made of 4mm sheet metal and needed to be studied in order to ensure that the tool would not distort. The hex socket plate also needed to withstand the force needed to separate the T-piece from the high-pressure shaft. Both of these parts required complex FEA analysis. The bolts used in removing the T-piece also would experience an impact force. Calculations for the minimum bolt size and the fatigue life cycle were performed in order to ensure that the design was adequate. Here we have the U-tool analysis. After constraining the tool to mimic the real-life force application, the maximum stress was found to be 13.62 megapascals, with a factor of safety of 13. The maximum stress and minimum factor of safety were studied for the hex socket as well. A maximum stress of 6.34 megapascals was found, with a minimum factor of safety of 55. Bolt impact analysis was performed using the worst-case scenario for each variable. A grade 10.9 12mm bolt was used based on the minimum bolt size calculations, and fatigue life cycle calculations determined that even with all variables assumed to be at their worst case, the bolts could be expected to last over 47,000 cycles. After project design was completed, the specifications were met for the disassembly station, and the design was approved by Bosch for future implementation. Due to current circumstances, the originally planned build of the station could not be performed. Additional consulting was performed for further process improvement in place of performing the build. Thank you for your time. Please feel free to ask the team members any questions you may have.